Welcome to Math's Zone African Motives. Today, we're diving into Activity 4.3, where we'll explore the world of circles, ellipses, hyperbolas, and semicircles. By the end of this tutorial, you will be able to sketch various conic section graphs, determine their domains and ranges, and understand concepts like symmetry, continuity, and inverse functions in the context of these graphs. Let's get started with our first question. Question 1 asks us to sketch the graph of the equation 6 squared plus 6y squared minus 150 equals 0, and then answer 3 follow-up questions. First, let's analyze the equation. We have 6x squared plus 6y squared minus 150 equals 0. The fact that both the x squared term and the y squared term have the same positive coefficient, which is 6, is a key indicator. This equation represents a circle. To make it easier to work with, let's rewrite it in the standard form of a circle, which is x squared plus y squared equals r squared. First, we add 150 to both sides of the equation. This gives us 6x squared plus 6y squared equals 150. Next, we divide every term by 6 to isolate the x squared and y squared terms. 6x squared divided by 6 is x squared. 6y squared divided by 6 is y squared. And 150 divided by 6 is 25. So our equation becomes x squared plus y squared equals 25. Now this is clearly the standard form of a circle. By comparing it to x squared plus y squared equals r squared, we can see that r squared is 25, which means the radius r is the square root of 25, which is phi. Since the equation has no x or y terms, we know the center of this circle is at the origin, the point 0, 0. So we have a circle centered at the origin with a radius of 5. Now let's sketch it. We draw our Cartesian plane, place our compass at the origin, set its radius to 5, and draw our perfect circle. This circle crosses the x-axis at 5 and 5 and the y-axis at 5 and 5. Now that we've sketched our graph, let's answer the questions. Question 1.1 asks for the domain of the graph. The domain represents all possible x values that the graph covers. Looking at our circle, we can see it spans from an x value of 5 on the left to an x value of 5 on the right. Every point on the circle has an x-coordinate somewhere in this interval. So the domain is the closed interval from 5 to 5. We write this as 5, 5. In other words, is greater than or equal to 5 and less than or equal to 5. This means all real numbers between and including 5 and 5 are part of the domain. Next, question 1.2 asks whether the graph is a function or a relation. Let's recall the definition of a function. A relation is simply any set of ordered pairs. A function is a special kind of relation where each x value corresponds to one and only one y value. In simpler terms, for any input, there is exactly one output. We can test this graphically using the vertical line test. If a vertical line crosses the graph more than once, the graph is not a function. If it crosses at most once for every x value, it is a function. Let's draw a vertical line, say at x equals 3. As you can see, this vertical line intersects our circle at 2 distinct points. This means that for the x value of 3, the circle has 2 different y values. Since one x value corresponds to 2 y values, the vertical line test fails. Therefore, this graph is not a function. It is a relation. So, our final answer for 1.2 is that the graph is a relation. Moving on to question 1.3, is the graph symmetrical about both axes? Symmetry means that one half of the graph is a mirror image of the other half. We can check for x-axis symmetry, y-axis symmetry, and even origin symmetry. Let's first test for symmetry about the y-axis. The rule for y-axis symmetry is that replacing x with negative x in the equation should result in an equivalent equation. Our equation is x squared plus y squared equals 25. If we replace x with negative x, we get negative x all squared, plus y squared equals 25. Since squaring a negative number gives a positive, negative x squared is just x squared. So the equation remains x squared plus y squared equals 25. The equation didn't change, so the graph is symmetrical about the y-axis. You can visualize this. The right side of the circle is a perfect mirror image of the left side. Now let's check for symmetry about the x-axis. The rule is to replace y with negative y. Replacing it with negative y, we get x squared plus negative y, all squared equals 25. Squaring negative y gives y squared. So again, the equation remains x squared plus y squared equals 25. Since the equation is unchanged, the graph is also symmetrical about the x-axis. The top half is a mirror image of the bottom half. Therefore, the answer to 1.3 is yes. The graph is symmetrical about both the x and y axes. Let's move on to question 2. Here we have two graphs to sketch. We'll start with 2.1, y equals the negative square root of the quantity 16 minus x squared. This equation looks a bit like the standard form of a circle, so let's try to manipulate it to see if it is. The first step is to get rid of the square root. We can do this by squaring both sides of the equation. So, we square y and we square the negative square root of 16 minus x squared. On the left, we have y squared. On the right, the negative sign becomes positive when squared, and the square root and the square cancel each other out, leaving us with 16 minus x squared. Now, let's rearrange this to look like a circle's equation. If we add x squared to both sides, we get x squared plus y squared equals 16. This is the equation of a circle centered at the origin with a radius of the square root of 16, which is 4. So the equation we were given represents part of a circle. But which part? Let's look closely at the original equation again. Y equals the negative square root of 16 minus x squared. This negative sign in front of the square root is very important. The square root symbol by convention always refers to the principal or positive root. So, the quantity radical 16 minus x squared is always non-negative, meaning it's greater than or equal to 0. Since y is equal to the negative of something that is never positive, the value of y must always be negative or 0. This means our graph is not the whole circle. It's only the lower semicircle, or the bottom half of the circle. Let's sketch it. We draw our axes, place our compass at the origin, set the radius to 4, and then only draw the arc that lies below the x-axis. This arc connects the point -4, 0, the point 0, -4, and the point 4, 0. And there is our graph of the lower semicircle. Y equals negative radical 16 minus x squared. Now for 2.2, x equals the square root of 9 minus y squared. We'll follow a similar process. This time, we need to square both sides to remove the square root around y. Squaring x gives x squared. Squaring the square root of 9 minus y squared gives 9 minus y squared. So we have x squared equals 9 minus y squared. Rearranging this into the standard form of a circle, we add y squared to both sides. This gives us x squared plus y squared equals 9. This is a circle centered at the origin with a radius of the square root of 9, which is 3. Once again, the original equation specifies a part of this circle. Let's look at the signs. The original equation was x equals the positive square root of 9 minus y squared. This positive sign in front of the square root means that x must always be positive or 0. This represents the right semicircle. So, our graph is the right semicircle. It's the half of the circle that lies to the right of the y-axis. It connects the point 0, -3, the point 3, g, and the point 0, 3. And there is our graph for question 2.2. Notice the importance of that sign in front of the radical in determining which portion of the circle we're dealing with. Question 3 asks us to sketch the graph of 4x squared minus 100 plus 25y squared equals 0 and answer 3 questions about it. Let's start by rewriting the equation to figure out what kind of graph it is. We have 4x squared plus 25y squared minus 100 equals 0. Notice the coefficients of the x squared and y squared terms. One is 4, the other is 25. They are both positive but different. This is the hallmark of an ellipse. The standard form of an ellipse is x squared over a squared plus y squared over b squared equals 1. To get our equation into this form, we need to make the right side equal to 1. So we divide every term in the equation by 100. 4x squared over 100 simplifies to x squared over 25. 25y squared over 100 simplifies to y squared over 4. And 100 over 100 is 1. Our standard form equation is x squared over 25 plus y squared over 4 equals 1. Now we can identify the key features of the ellipse. The larger denominator, 25, is under x squared. This means the major axis is horizontal. We know that a squared equals 25, so the length of the semi-major axis, A, is 5. This tells us the ellipse extends 5 units in both the positive and negative x directions from the center. The smaller denominator, 4, is under y squared. We know that b squared equals 4, so the length of the semi-minor axis, b, is 2. This tells us the ellipse extends 2 units in both the positive and negative y directions. Now let's sketch it. We draw our axes, center our ellipse at the origin, go out 5 units left and right, and 2 units up and down. Then we connect these points to form our ellipse. This graph crosses the x-axis at 5 and 5, and the y-axis at 2 and 2. With our ellipse sketched, let's answer question 3.1. Is the graph continuous or discontinuous? Informally, a graph is continuous if you can draw it from end to end without lifting your pencil. A graph is discontinuous if it has breaks, jumps, or holes. Looking at our ellipse, there are no gaps or jumps anywhere. It's a single, unbroken curve. So, yes, it is continuous. So the answer for 3.1 is that the graph is continuous. Next, question 3.2 asks for the range of the graph. The range is the set of all possible y values. We can determine the range by looking at the vertical extent of our ellipse. Our sketch clearly shows that the ellipse reaches a maximum y value of 2 and a minimum y value of 2. It covers every y value in between. The graph is bounded vertically by these 2 values. So, the range of the graph is the closed interval from 2 to 2. We write this as +2, 2, which means all real numbers greater than or equal to 2 and less than or equal to 2. Finally, for question 3.3, does this graph have an inverse function? For a graph to have an inverse function, it must first be a function itself. We can check this using the vertical line test. As we can see, if we draw a vertical line, it intersects our ellipse twice. For example, the line x equals 2 intersects at 2 distinct points, 2, 1.83, and 2, 1.83. Since one x value corresponds to 2 y values, the ellipse is not a function. The condition for having an inverse function is even stricter. It must be a one-to-one function, which means it must pass both the vertical line test and the horizontal line test. Since our ellipse isn't even a function, it cannot possibly be a one-to-one function. Therefore, the answer is no. The graph does not have an inverse function. We're halfway through. Let's tackle question 4. We need to sketch the graph of xy equals 12 and then answer 3 more questions. The equation xy equals a constant is the definition of a hyperbola. Let's rewrite it in the more familiar form y equals m over x. Dividing both sides by x, we get y equals -12 over x. This is an example of a reciprocal function. Its graph is a hyperbola. This graph has 2 special lines called asymptotes, which the graph approaches but never touches. For a function of the form y equals k over x, the asymptotes are the x-axis and the y-axis. So we have a vertical asymptote at x equals 0, the y-axis, and a horizontal asymptote at y equals 0, the x-axis. Because our constant k is -12, we know the branches of the hyperbola will be in the second and fourth quadrants. Let's find a couple of points to help us sketch. Let's choose a few x values. If x equals 2, y is -12 over 2, which is -6. So we have the point 2 to 6. If x equals -3, y is -12 over -3, which is 4. So we have the point 4. Now we sketch the graph. We draw our asymptotes, the x and y axes. We plot our points 2 to 6 and 3, 4. Then we draw the 2 branches of the hyperbola. One branch curves through 3, 4, approaching the asymptotes but never touching them. The other branch curves through 2, 6, also approaching the asymptotes. Question 4.1 asks us to state the lines about which the graph is symmetrical. Unlike circles and ellipses, hyperbolas of the form xy equals a constant have 2 different lines of symmetry. The first line of symmetry is the line y equals x. If you were to fold the entire plane along this line, the 2 branches of the hyperbola would perfectly overlap. Let's test this algebraically. We replace both x with y and y with x. This gives us yx equals -12, which is the same as xy equals -12. Since the equation doesn't change, the graph is indeed symmetrical about the line y equals x. So our first line of symmetry is y equals x. The second line of symmetry is the line y equals negative x. This line acts as a mirror that transforms one branch of the hyperbola into the other. Let's test this algebraically. We replace x with negative y and y with negative x. This gives us negative y times negative x equals negative 12. Negative y times negative x is positive xy, so we have xy equals negative 12. Again, the equation is unchanged. So our second line of symmetry is y equals negative x. These are the two lines of symmetry for this graph. To summarize, the graph is symmetrical about the lines y equals x and y equals negative x. Question 4.2. Does this graph have an inverse function? Remember, for an inverse function to exist, the original function must be a one-to-one function. This means it must pass both the vertical and horizontal line tests. First, let's perform the vertical line test. If we draw a vertical line anywhere to the left or right of the y-axis, it will only intersect one of the hyperbola's branches at a single point. It never intersects both branches. So, the graph passes the vertical line test and is a function. Now, let's apply the horizontal line test. This test checks for one-to-one correspondence by seeing if any horizontal line crosses the graph more than once. If we draw a horizontal line anywhere above or below the x-axis, it also only intersects one of the branches at a single point. For any given y value, there is only one corresponding x value. So, the graph passes the horizontal line test. Since the graph passes both the vertical and horizontal line tests, it is a one-to-one function. Therefore, it has an inverse function. A quick interesting fact, the inverse of y equals k over x is itself. If you swap x and y and x equals negative 12 over y, you get y equals negative 12 over x, which is the original equation. So the answer to 4.2 is yes. This graph has an inverse function. Question 4.3 asks for the domain and range of this graph. Let's find the domain first. The domain is all possible x values. Looking at the graph, the x values extend infinitely to the left and infinitely to the right. However, there's a problem at x equals 0. The graph never crosses or touches the y-axis because it's a vertical asymptote. The domain is all real numbers except for x equals 0. We can write this in set notation as the set of all real numbers r excluding 0. This is the correct domain. Now let's determine the range, which is all possible y values. Similarly, the graph extends infinitely upwards and downwards, but it never crosses or touches the x-axis, which is the horizontal asymptote at y equals 0. The range is all real numbers except for y equals 0. In set notation, this is the set of all real numbers r excluding 0. This is the correct range. Our final question is number 5. We need to sketch the graph of 2x squared equals 36 plus 6y squared and answer 3 questions about it. Let's begin by reorganizing the equation to identify the type of graph. We have 2x squared equals 36 plus 6y squared. The key feature here is that one of the squared terms is positive and the other is negative. In this case, 2x squared is positive, and 6y squared becomes negative if we move it to the left side. This is the definition of a hyperbola, not like the one in question 4, but the type with a minus sign between the squared terms. The standard form of this hyperbola is x squared over a squared minus y squared over b squared equals 1. To get our equation into this form, the right side must be 1. So, we divide the entire equation by 36. Dividing by 6, we get 2x squared over 36 minus 6y squared over 36 equals 36 over the 6. This simplifies to x squared over 18 minus y squared over 6 equals 1. Because the x squared term is positive, this is a horizontal hyperbola. It opens left and right. We can identify a and b. A squared equals 18, so the distance from the center to a vertex, a, is the square root of 18, which is approximately 4.243. B squared equals 6, so b is the square root of 6, approximately 2.449. The center is at the origin. To sketch, we draw our axes. The vertices are at plus or minus 4.243 on the x-axis. Using a and b, we can find the equation of the asymptotes, which are y equals plus or minus b over a times x. The lines are y equals plus or minus 0.577x. We sketch these lines and then draw the hyperbola's branches opening left and right, passing through the vertices and approaching the asymptotes. Now let's answer the questions. First, 5.1. Is the graph symmetrical about the y-axis? For y-axis symmetry, the left side of the graph must be a mirror image of the right side. Our hyperbola opens left and right, with its branches symmetrical about the y-axis. The right branch is a reflection of the left branch, so the answer is yes. The graph is symmetrical about the y-axis. Question 5.2 asks us to state the domain and range of the graph. Let's start with the domain, the x values. Looking at the horizontal extent of the graph, we can see it exists from negative infinity up to the vertex at x equals negative radical 18, and then from the vertex at x equals positive radical 18 to positive infinity. The graph does not exist in the space between the vertices, so the domain is the union of two intervals. The first interval is from negative infinity to negative radical 18, inclusive. The second interval is from radical 18 to positive infinity, inclusive. Remember, the square root of 18 is approximately 4.243. Now for the range, the y-values. Looking at the vertical extent of the graph, we can see that the branches extend infinitely upwards and downwards. Every y-value is covered by at least one point on the graph. There are no gaps in the vertical direction. Therefore, the range of the graph is all real numbers. We write this as r. Finally, question 5.3. Is the graph continuous or discontinuous? Remember, a continuous graph can be drawn without lifting your pencil. If you look at our hyperbola, it consists of two separate, distinct branches. To draw the entire graph, you would have to lift your pencil from one branch to move to the other. There is a clear gap or break in the graph between the two branches. Because of this break, the graph is discontinuous. So, the answer for 5.3 is discontinuous. And that concludes Activity 4.3. We've worked through sketching a variety of conic sections, including circles, ellipses, hyperbolas, and semicircles. We've learned how to identify these curves from their algebraic equations, put them into standard form, and use that information to sketch their graphs. We also practiced finding the domain and range, testing for continuity and symmetry, and determining if an inverse function exists. You should now be able to confidently solve problems involving these fundamental graphs. Thank you for watching. Subscribe to Math Zone African Motives for more tutorials.